All right, cool. So my name is Neehar. Thanks, Akshay, for the intro. We're going to talk a little bit about something that's a little bit on the bleeding edge, but at the same time is also really, really old, and it's reason. Um, what are my objectives with this talk? My objectives with this talk is to convince all of you to write functional code. Are the objectives of my talk to make sure that all of you leave here as converts to the cult of the reason programming language? Actually not, as you might have guessed from the title of my talk. I actually want to convert all of you into Hoobastank fans. How many of you have heard, and the reason is you back in college? My stated objective is really simple. I want to get the song stuck in your head before this talk is over. So let's go through what reason is. Reason is not a new programming language. That's a distinction I want to make upfront very, very clearly. Reason happens to be a new wrapper, a new syntax, a new sort of tool chain around this slightly academic programming language called OCaml. How many of you have heard of OCaml? It's been around for a really, really long time, but no one's ever used it for front-end development before. But there's been a couple of recent developments that have happened, excuse me, which have allowed this. Let's see what those are. Sorry, Akshay, can I get the timer working? Sorry. So first of all, there was a very old programming language called Caml, which a bunch of people sort of sitting in France decided to work on. Then it got changed into this language called Caml Lite, which had a bytecode interpreter. It had a VM, pretty straightforward stuff. Then it changed to Caml Special Lite, which also had a compiler that could spit out native code and not just bytecode for the VM. And we all know compiling to native code is much faster. But then something very interesting happened. Along came this language built on top of all of this called OCaml. And OCaml actually stands for Objective Caml. And one of the thoughts behind it was, what if we take this functional language of Caml and allow people to write some object-oriented code in it as well? Be a little bit more pragmatic. Let's not be sort of these priests of functional purity, right? So along came OCaml, which lets you sort of dig into the imperative parts if you want to, while still giving you all of the benefits of a statically typed, a strongly typed functional programming language. And then 20 years later, there was this project that was open source called BuckleScript by Bloomberg. And BuckleScript is very interesting because BuckleScript enabled this 25-year-old programming language, which could do all sorts of interesting things, to actually emit JavaScript. Pretty neat, right? And then in 2017, Facebook open sourced Reason. And what Reason essentially is take the OCaml language, we can have it spit out JavaScript, but hang on, this sort of 25-year-old functional programming language, this syntax is kind of off. You know, for a bunch of us who come from a very web development environment, we like the way our JavaScript is written. We like our brackets. We like seeing things in a certain way, right? So why don't we take this old functional programming language and make the syntax a little easier for JS devs to understand? Because that's always been the difficult part, right? We can bike shed indefinitely over this language has referential transparency, this language has Y, but at the end of the day, if it looks like garbage, I'm not going to write in it. That's the truth. That's what it all boils down to. Does it look pretty enough for me? Does it look readable enough for me? So that's what Reason does. Very simply, OCaml can spit out bytecode or it can spit out native code. We replace the OCaml compiler or the backend of the OCaml compiler with BuckleScript, which takes the OCaml syntax, constructs an abstract syntax tree out of it, and then spits out bytecode native. We make it instead generate JavaScript, and then we update the syntax. So we've taken this old way of doing things and got a brand new way where you've got a functional programming language giving you JavaScript. Now this is the how. Let's get into the why. So Reason and BuckleScript are sort of evil twin sisters working in tandem together. While you can use Reason with other OCaml backends as well, it's by far the best ways to use BuckleScript because it's just amazing. So quick recap, Reason is a new syntax for a very old programming language, OCaml. You can use both the entire JavaScript ecosystem as well as the OCaml ecosystem, right? You're talking about a 25-year-old programming language and the plethora of libraries that have been developed for many, many decades that you can use in your front-end code or your server-side code today, and you're talking about the entire NPM ecosystem. Bring those two together, get functional, sort of the advantages of a functional language, and you get Reason. Who remembers the chorus of the song? And the reason is you. This is pretty much what it is, right? I told you I'm going to get it stuck in your head. So essentially, this is what it is, right? I found a reason for me and blah, blah, blah. And what is the reason, right? First of all, the reason is type safety. The reason you want to use a functional programming language or you want to use strongly typed programming languages, you want type safety. Prashant did an excellent talk on TypeScript, and I'm pretty sure he sold you on types and how important they are for your front-end development. Types aren't meant to make writing your initial code easy, as far as we know. Types are meant to make your code easy to refactor. That's been the case always. One of the biggest reasons why we haven't jumped into writing types so much is because it's so verbose, writing it out. But Reason solves that in a very intuitive way because it has a world-class type inference system. You actually need to write very few types with Reason, and we're going to see how that works. The reason is performance. One of the advantages that you get with having the compiler itself written in OCaml, the compiler that converts Reason into JavaScript, is that it's actually compiled to native code. So you have a native binary which is compiling your functional language into your JavaScript code, which is blazingly fast. In fact, some of the times when I run it on about, say, a few thousand lines of code, you're looking at sub-second compile times. And this is not even in watch mode. And for those of us who are used to, Babel and Webpack and just, sort of staring at our computer screens while we go get a coffee while our build is running, this is a godsend. One of the other aspects of performance we'll also discuss is the fact that because of the deep static analysis the compiler can do, it actually ends up emitting very optimized JavaScript. It's also pragmatic. Remember what I said, that OCaml is objective camel. So if you as a JavaScript developer don't want to drink this Kool-Aid of I need to write functional code anywhere and everywhere, but you actually want to say, you know what, I may not feel and I may not sleep well at night, but I do want to write some like hacky imperative code, go ahead and do that. The compiler's got your back. It's also phenomenal tooling. We'll see some examples of that, where one of the advantages of Reason is it brings together several different tools from the OCaml ecosystem for you to get a great type system, great editor integration, and stuff like that. It's also interop. For any compile to JavaScript language, one of the most important things has to be, wait, I already have an existing project. How do I sort of use this new goodness with my existing code, right? And one of the ways that you end up being able to do that is because Reason gives you a way to interop with your existing JavaScript code. And all of this put together ends up giving you really good developer experience. One of the biggest points that I want you to take away from this entire talk is that if you use Reason, you will be more productive while at the same time not sacrificing any of the developer experience that you're accustomed to. So let's go through the type system in a bit more detail. I won't go into as much detail as sort of the TypeScript talk because there's a lot more to talk about here as well. Firstly, it's sound. What do you mean by a sound type system? It simply means that you're not, the compiler, when it's sort of checking your types, it's not trying its best. If the compiler says that your program compiled successfully, all the type checks have passed, it is bug-free. You've covered everything. It's sound. It is not going to make a mistake. It's inferred, which means a lot of common patterns that you'd see in other sort of languages with types where you explicitly have to write a lot of types, you don't need to do that in Reason. The compiler is sort of almost like a pair programmer with you, and it automatically infers a lot of very interesting things. There's 100% coverage. So if you've ever used Flow or TypeScript, you also have to know how much of your code is actually covered by the compiler. That's not the case in Reason because everything has a type. It has to have a type, right? So you're never in a situation where you have some parts of your code which are typed and some parts of your code which are untyped. Everything is fully covered. And lastly and most important, it is fully buzzword compliant. You want algebraic data types, you want generalized algebraic data types, you want sum types, you want union types, you want parameterized variants, whatever buzzwords you've read about on the internet, we've got it covered, right? So if you want to convince someone and throw like a lot of acronyms around, this is the way to do it. I know the font size is slightly small. Can the people at the top sort of see this? Can the people at the back see this? Okay, quickly going to switch over to my editor and hopefully that. So this is an example of how you type Reason code out. Do you guys notice the very interesting thing where there's a type sort of automatically inferred at the top? And this is something that just works out of the box, right? Is this better? So all of this is stuff that as I am typing out, right, it's automatically figured out it's an array of string, right? So you don't need to annotate, you don't need to say that this is an array of numbers, you don't need to say any of that. The compiler figures this out, which is the way types should be written, right? Why do we have to tell the compiler so much? It should be our best friend. And there's tons of little interesting things you can do like this. Here's an example of okay, here's an interesting thing. Now, one of the most, as JavaScript developers, one of the things that we do the most is we work with objects, right? Think of objects as records. That's the term that we use in Reason, which are strongly typed. So you define your record type over here. I'm saying type doc has a title and a length. Now, usually what you would assume is that if you had to write any functions that deal with this type, or if you had to write any code that deals with this type, everywhere in your code you would have to say, okay, this thing that I'm doing, it's of type doc, right? You don't need to do that in Reason. You just write it just like you would any other JavaScript object. It automatically looks at the shape of your object and figures out that the type it corresponds to is doc. That's it. You don't have to annotate it at all. And this is beautiful. This is the way it should be, right? Why should we sort of, obviously there are a few edge cases with this where if you have types which are very similar, you still need to annotate it. But in my experience, the vast majority of code that you're writing, the compiler just gets out of the way. And let's say you write a function. So here I have a really simple function called trim talk length. Now look at the syntax. How many of you think this looks very similar to JavaScript? The function. It's equal to it just, we've just used fun instead of function, right? That's about it. And I'm doing a spread operator over here. And there's no return statement. Because in a functional language, everything is an expression. The last line is your return statement, right? And look at the type signature of this function. It's automatically inferred without me annotating a single thing that this takes in a talk, a value of type talk, modifies it slightly and returns it. So you get all the goodness of types that we saw in the earlier talk, and we generally know types are good for us without the verbosity of writing it out, which is the holy grail. Right? Let's look at something interesting that is born out of the type system and other interesting things in the language. Pattern matching. How much of our JavaScript code ends up being switches and if-elses? Pretty much most of it, right? Any conditional branching logic that we need to do, it ends up being that. How can we have the compiler help us with that? So this is a pretty simple recursive factorial function. This is how most of us learned. It's a really bad way to write it because you'll get a stack overflow, but still, this is how you do a recursive function. Here, I've used a slightly different syntax, which is a little, just to sort of illustrate that there are two ways to write functions in Reason. So here, this is the name of the function. This is the value that we're passing. I've omitted the function keyword. This is like a shorthand notation to write it. You can also write it in the more JavaScript similar way if you feel more comfortable with that. Again, it's completely up to you. And here, I switch the value, right? And I say if it's 0, return 1. If it's n, do n into factorial n minus 1. Pretty straightforward. This is how you do a simple factorial function. How does the compiler help us with this? What if I forget the case where if it's n, multiply n into factorial n minus 1, right? I get a warning here. Okay, fair enough. Maybe the compiler can figure out that there's something wrong with this switch that you're doing. And remember, here we're switching on the value of the thing that we're passing into the function. But here's what's really cool. When you run this, right, the warning that the compiler gives you is not that there's something wrong with your program. This is the part that I want to highlight. The compiler actually tells you you forgot to handle a possible value here for example 1. It's actually giving you a value that you can input into your function which you haven't covered in your code. This is literally the example of someone sitting next to you and saying, bro, tune ye nahi kiya. You've forgotten this case. This is what compilers were meant to do, but somewhere along the line they became these monstrosities that only serve very obscure error messages, right? The first time I saw this, it blew my mind. And I was like, agile what, pair programming what, I just need a really good compiler. Right? So pattern matching is cool, right? You know what's cooler? Is pattern matching with types. What if we can take these types and we can do interesting things with pattern matching with them? Here's a slightly, this is an example from a thing that I've been working on. It's a little verbose, but bear with me. It's a huge amount of code. We'll go through it very quickly. The first is I have a simple phone number, right? Which says that I can have 3 types of phone numbers. There is no phone number. There's a phone number stored in the international E164 format, which is just a string plus 91 something something something. Or in some legacy system of ours, we actually stored country code and phone number separately. All of us have been in this situation. We have backend systems which have different formats. Then those formats update. Then in the front end code, we have to change a bunch of things. We have to write a huge amount of if-elses to handle all of this. So what do we do here? We define a type, right? This is known as a variant. And we say that our phone number can be none or this or this. And the two sort of inputs that you see to the variant are called, this is like a constructor. We're saying that E164 takes in a string, does something with it. The legacy phone number takes an int and a float and does something. So here I'm just going to define the three. New phone number just takes in a string. Legacy phone number takes an int and a float because it's going to be pretty big. And no phone number is just none, right? It's just that this person doesn't have a phone number. Now let's say you need to write a function to format this phone number, right? And display it very nicely to the user in a standardized way. This is how I'd write something like this. We switch on the value, we switch on the type. And we say when he doesn't have a phone number, we send him a really nice message. When he has a legacy one, if you notice, we are able to take the int and the float that we are passing to legacy format and rename them as prefix and number. So we can have nice looking names there as well. String of int is a very simple function to convert string to an int. And string to float, and this is how we end up formatting the whole thing. And if it's E164, it's already a string, just display that as is. We log it. This is what the output looks like, right? This is pretty cool. We've just taken a bunch of our if-else logic, written it a bit more concisely. That's nice. Not too different from JavaScript. How can the compiler help us? Imagine I remove the case where I don't handle the case where there is no phone number. Here the compiler is immediately going to tell you forgot to handle a possible value when there is no phone number. That's it. Now I know that I need to sort of handle that case as well. Why is this useful as well for refactoring? Imagine tomorrow your backend team comes to you and says, we have decided on our own custom in-house phone number because we know better than the rest of the world, right? We've all worked with backend devs like that. And then they come up with a brand new spanking format which is unlike anything anyone has ever seen, right? Now, you need to handle that case everywhere in your code. How do you do that? You just have to update your initial type definition for phone number. The compiler will tell you every single place, whether that's format phone number, whether that is add phone number, whether that is take phone number and display it in emoji, whatever are the functions that you've written, the compiler knows all those places it will tell you that you haven't handled this new format, right? Pretty neat. Now let's get into performance really quickly. So one of the obvious things that I talked about is how fast it is. Also, because it's able to do a lot of very complex static analysis, it does dead code elimination. And more importantly, it pulls in very, very little runtime. Most compiled to JS languages to preserve the semantics of the original language pull in a huge amount of runtime JavaScript to sort of keep the environment the same. But one of the reasons that reason was invented, see what I did there, is the fact that OCaml and JavaScript in a lot of cases have a 1:1 similarity, right? Whether that's switches, whether that's objects, whether that's arrays, whether that's let binding. So in a lot of places, you're able to very simply translate things over without needing to pull in any of the runtime. Let's take a look at how that looks. I'm looking at our factorial function again, the similar one that we saw earlier. When I compile this, what does the output look like? My magic compiler, if any of you are Twin Peaks fans, right? And this is the output. But hang on a second. I just sold you on how there's minimal runtime. But why is the code so big, right? Does anyone know? JavaScript doesn't have integers, right? So we're still, when it compiles that code, it wraps all of that code with sort of integer multiplication and stuff like that to preserve the semantics of integer code, right? So it ensures that safety. But what if we were to rewrite our factorial function using floats, because JavaScript only has floats, right? So I've done a bunch of float operations over here. You just have to annotate it with a dot, your multiplication and negation or whatever. This is the compiled output. If you remove the top comment and the bottom comment, I can guarantee to you none of you would realize this has been spat out by a compiler. This is exactly like any of us would write the code, right? And this scales to thousands of lines of code, not just a simple factorial example. So one of the biggest selling points of Reason and one of the coolest things about it is that you don't have to treat the compiled JavaScript as some sort of build artifact. Write your code in Reason, let it spit out JavaScript, check the JavaScript into your source folder, and have the other people in your team who don't know functional languages use that JavaScript, because they can look at this file and understand what it is without knowing to know Reason and understand that. So this makes it very easy in large teams for you to start adopting it incrementally, right? I mean, this first time just like what the hell's going on, right? All right, it's also very pragmatic in terms of it gives you a lot of escape hatches to interop with JavaScript, to write imperative code. I'm going to skip over some of this stuff because it's a little dense and also because we have a lack of time, because there's one very important thing I want to talk about, right? How do you do interop? Pretty straightforward. If you want to use reason from your existing JavaScript, just compile reason to JavaScript, use it. If you want to use existing JavaScript in your reason code, you basically have to summon the old gods, perform an arcane ritual, and sort of pray for the best. But essentially, there's a way to do it using something known as a foreign function interface. One quick note about reason is that it was invented or put together by Jordan Walk, who is also the inventor of React. When originally React was written, it was written in a language called SML, but they very quickly realized that React wouldn't be adopted very widely if it was written in an obscure ML language. So it was converted into, or you could write it in JavaScript. But now we have the tooling with BuckleScript and stuff like that to actually use React the way the authors of it originally intended, which is using ReasonML. So it's the same team that's built both. So if you're getting into React development, I definitely check out Reason React. It has a beautiful API, which you can sort of quickly see here, where everything is sort of pure functions to be able to do it, and that's something that you can dive into, right? This is FFI, which is how do you deal with existing JavaScript. This looks super historic and complicated, but what I want to point out to you is this is the JavaScript that's generated, right? Reason doesn't understand what document is or what get element by ID is, but you can write an interface that compiles to this JavaScript, which again looks completely handwritten, right? Pretty cool. Now, the thing that I'm most excited about for Reason is not the fact that I can write type safe, pattern matching, I can do all these cool things today. The reason I'm most excited about it is the future. What happens? So currently this is how Reason works, right? We compile to JavaScript, which we can run in a browser, we can run it in Node. But remember at the very beginning of my talk, I said that OCaml has a brilliant native, compile to native sort of process as well. And the BuckleScript compiler itself is also written in native code. So what if we could take the Reason compiler or the OCaml compiler and have it on the server side generate a binary for us? Imagine you're writing isomorphic web applications where you're sending client-side JavaScript, but your server is an absolutely, completely optimized tiny binary. OCaml code when compiled to native, I have seen servers that start up in 6 milliseconds, right? Imagine the kind of performance we can get out of that. And imagine the future where the same compiler is giving you binary for the front end and binary for your server. So you write type safe code, which compiles to JavaScript if you so feel like it, or actually compiles to all of the possible places it can be deployed in binary. Basically what I'm trying to tell you is we have reinvented Java after all these years. Write once, run anywhere, except not in bytecode, but in binary. There are still a few things left for WASM to be ready. There's garbage collection and tail call recursion optimization, stuff like that left, but we're very, very close to this. And we as JavaScript developers now have access to writing code in a functional language where the types are inferred for you, where the syntax isn't that different and it feels familiar to us, and to actually deploy native code, right? You don't have to feel like the Rust guys or the C++ guys are better anymore or doing some sort of historic magic, right? We can do this. And that's why I'm most excited for Reason. That was my talk. Couple of quick shout outs to a few friends, Ankur and Sanders Pease from Twitter for helping me with feedback from this. And thanks to the organizers and all of you for listening to this. And I hope I've got the song stuck in your head, and I hope I've given you a reason to try out Reason. Thank you so much. I can maybe take like 8.
We have time for just one question, which is from Jen.
Can the question just not be on the patents, React Reason patents?
It was just on error messages.
Yes.
So like runtime error messages.
Right.
So you know, basically you write your code in Reason and it gets compiled to like JavaScript.
Correct.
And let's say we get a runtime error.
Correct.
So how do I extrapolate that error back into Reason code? So, how good is it? That
okay, there's a couple of things there. If because of the fact that your code is strongly typed, if it's going to be entirely Reason code, you're not going to get a runtime error. That's just not going to happen. If you've ever written Elm code or any of that sort, you just don't get runtime errors because you've covered every single possible case. As long as you model your types correctly, right, and you say that this value cannot be present as well, you will never get undefined as not a function. You will forget that phrase even existed, right? But if you do end up getting a runtime error because you're mixing your strongly typed Reason code with sort of some of your untyped JavaScript code, because of the nature of how Reason compiles to JavaScript, right, and it doesn't spit out sort of code that looks very obscure and stuff like that, in my practical experience, it's very easy to go back and just do a 1:1 mapping because I know exactly where this has come from. because it looks very similar, because the variable names are preserved firstly, right? The file names are also exactly preserved, and it even tries to make sure that if you're using a particular data structure, it'll try to preserve the same data structure. And the compiled code also has extensive comments on what is the equivalent name of the thing in reason. So it becomes pretty easy for you to figure out where did it come from.
Thank you. Thanks, Neehar.
Okay, any other questions? Happy to meet you guys outside. Come fight me on this. Thank you.